This video is endorsed by Untitled.
Hello, welcome to Paul Academy. In today's video, we will be highlighting and correcting some common mistakes found in each of the units of the IB1 Chemistry course. Not in IB Chemistry? Don't worry, these tips will help you too. This video is presented by Leonard Cohen, Jeffrey, and TNC. Oops, I meant to say Aaron, Jonathan, and William.
Category A is exam skills and prep. So during this segment of the video, I'll just be giving a few tips that I hope will help you guys out for the exam. Tip number 1. Familiarize yourself with IB command terms. Now IB has over 30 command terms, but for the purpose of this video, we'll be going over 6 that you guys will encounter a lot. State. Give a specific name, value, or other brief answer without explanation or calculation. List. Give a sequence of brief answers without explanation. Compare and contrast. Give an account of similarities and differences between two or more items or situations, referring to both or all of them throughout. Draw. Represent by means of a labeled accurate diagram or graph using a pencil. A ruler should be used for straight lines, diagrams should be drawn to scale. Graphs should have points correctly plotted and joined in a straight line or smooth curve. Explain. Give a detailed account including reasons or causes. Tip number 2. Use the Markscheme to your advantage. Let's take an example. Use 20 words or less to explain why ammonia readily forms complex ions with the transition elements, but the ammonium ion does not. Now, the most notable part of this is that you can see that this question is allotted 2 points only. So for 1 point, I would state that to form a complex ion, the ligand must be a Lewis base and must have at least one pair of lone electrons that it can contribute to the metal ion. For the second point, you draw the Lewis structure for ammonia, showing the lone pair, and the ammonium ion with the central nitrogen fully bonded. Tip number 3. Know your conversions. Know your unit conversions. So throughout the course, there's going to be many conversions that you're going to see on tests, some of them being 1 ton equals 1,000 kilograms, which equals 1 million grams. 1 cubic millimeter equals 1 million cubic centimeters. 1 milliliter equals 1 cubic centimeter, and 1 liter equals 1 cubic decimeter. Category B is moles and stoichiometry. What do you get when you cut an avocado into 6 times 10 to the 23 pieces? Guacamole.
Moles? You mean that weird thing that lives in the ground?
Tip number 1. Relative atomic mass versus molar mass. The molar mass of a compound tells you the mass of 1 mole of that substance. In other words, it tells you the number of grams per mole of a compound. The units for molar mass are therefore grams per mole. The relative atomic mass of an element is the weighted average of the masses of all the isotopes in the naturally occurring element, relative to the mass of an atom of the carbon-12 isotope. Most importantly, it has no units. Tip number 2. Oxidation numbers of diatomic molecules. It's 0. The oxidation number of an element in its free or uncombined form is 0. For example, aluminum. However, this is also true for elements found in nature that are diatomic, such as Hofbrinkel and sulfur, found as S8. Tip number 3. The sum of coefficients. So, let's take an example. Magnesium metal reacts with hydrochloric acid to produce hydrogen gas and aqueous magnesium chloride. So even though it isn't shown in the equation, it is implied that if there are no coefficients in front of a chemical formula, then you automatically know that there is a 1 there. Therefore, the sum of the coefficients in the balanced molecular equation is 1 plus 2 plus 1 plus 1, which is 5. Tip number 4. Ionic or covalent? Double check. So let's say we have metal X and non-metal O, and that they form X2O6. So normally we would think that this is ionic, right? Because it's metal and non-metal and it seems ionic. But that's wrong. Actually, it's molecular and it doesn't even exist. So molecular formulas only apply with molecular compounds such as hydrocarbons. Ionic compounds always form in the same ratio in a crystal lattice. So if it were to exist, it would exist as XO3. Tip number 5. Be clear and careful about moles. So an atom consists of a nucleus and some number of electrons. A molecule consists of 2 or more atoms bonded together. Therefore, when you are talking about moles, 1 mole of an oxygen atom is 16 grams, but 1 mole of O2 is 32 grams, because O2 is the oxygen molecule containing 2 nuclei.
Why can't I ever find the solutions to these acid-base questions?
So welcome to Category C, Acids and Bases, and these are some common mistakes you can make in this unit of our chemistry course. So tip number 1. So an example problem with the concentration of radium hydroxide being 0.784 molars. So what is the pH of the radium hydroxide solution? So we can use our equation. However, we need to remember that the formula is OH2, which means we have to double the concentration to account for the chemical formula. So tip number 2. So when we're looking at hydrogen bonding, we can look at a water molecule with the electronegativity difference and the dipoles, and we can circle here a hydrogen bond, but this wouldn't be a hydrogen bond because a hydrogen bond is an intermolecular force. So we can see it's between the 2 water molecules, an intermolecular force. So tip number 3. So we need to make sure we remember that a strong acid does not mean that it is concentrated. It could be dilute. However, a strong acid does mean that it's a strong electrolyte. It's fully dissociated. A weak acid is a weak electrolyte, partially dissociated. So tip number 4. So when we look at states in equations, we need to remember to have them and also to have the correct ones. So we can look at a sample equation with an acid and a carbonate to form a salt, water, and carbon dioxide. So the salt, in this case calcium chloride, is aqueous, dissolved in water. Salts are always aqueous, and this is important to remember. Tip number 5. So bond vs molecular polarity. So this can be seen in CO2 and water. So for carbon dioxide here we have the CO bond, there is a dipole moment there because of the strong electronegative difference. But the dipoles cancel because of the molecular geometry, compared to water with lone pairs where the dipoles don't cancel, and thus water is polar as a molecule. Tip number 6. So conjugate acids and bases. So we can look at a sample equation here with ammonia and water to form ammonium and hydroxide ion. So we can see here that water acts as an acid as it donates a proton. So the difference between an acid and its conjugate base is just 1 proton. Same with a base and a conjugate acid, 1 proton. Tip number 7. So amphiprotic. So this is a term to classify a species that is both an acid and a base. So we just looked at water acting as an acid. So we can also see here water acting as a base as it accepts a proton to form hydronium. So water acts as an acid and a base. Category D, gases. Tip number 1. So the volume of an ideal gas is 0. So we can see here in a container, would be 0. But when the actual answer is that the molecules themselves have a volume of 0. The container still has a volume. Tip number 2. So when we're using our ideal gas equation, PV equals nRT, always use kelvins for the calculations of temperature. So if you're given the degree Celsius in an equation, in a problem, convert to kelvins.
Category E is about correcting mistakes concerning atomic structure, periodic trends, and bonding. In the following two categories, blue subtitles will represent a concept, while red subtitles will represent an example question. Tip number 1. When water is boiled, what changes occur in the bonding between the hydrogen and oxygen atoms? The answer is simple, right? The covalent bonds break. Wrong. Covalent bonds are considerably difficult to break, requiring a lot of energy known as bond dissociation energy to be inputted, an amount that is not typically present in chemical processes. In short, we will not be discussing the breaking of covalent bonds in this course. So do not write that the covalent bonds are broken on a test. Your teacher will not be impressed and they will make fun of you for writing this. The correct answer is that IMFAs are broken, in this case hydrogen bonds and LDF. Tip number 2. Metallic bonding is a type of bonding occurring in, you guessed it, metals. Metallic bonding is the electrostatic forces of attraction between the cations, the positive kernels, and the negatively charged sea of electrons surrounding the kernels. The greater the number of electrons contributed to the sea by each metal atom, the greater the attraction in the metal bond, and therefore the melting and boiling points are higher. This is why sodium with one valence electron has a melting point of 97.8 degrees Celsius, while magnesium with two valence electrons has a melting point of 649 degrees Celsius. They are both in period 3. Tip number 3. We will discuss the difference between ionic bonding and covalent bonding. Ionic bonding is due to the electrostatic forces of attraction between the oppositely charged ions. Covalent bonding is the sharing of electrons by two atoms, meaning that no electrons are taken by either atom. Tip number 4. Now to nomenclature. Name the following compound, Fe2O3. Looks like iron oxide, right? Well, wrong. Iron is a transition metal, so it has multiple oxidation states, these being +2 and +3. While iron forms ionic bonds with oxygen to form oxides, it can be in either state. Therefore, it is necessary to specify in which state the iron is. Therefore, the correct name of Fe2O3 using the stock naming system is iron 3 oxide. Tip number 5. When hydrogen electrons are excited from their ground state, they will jump to higher orbitals. When they return to a lower orbital, they will release a certain amount of energy corresponding to a certain type of light on the electromagnetic spectrum. When returning to orbital n equals 1, known as the Lyman series, ultraviolet light is released since the energy between the first orbital to the second orbital is the greatest, while the energy difference decreases as more orbitals are added. When returning to orbital n equals 2, visible light is released. This is called the Balmer series, which will be the focus in this course. When returning to orbitals n equals 3, 4, and 5, infrared light is released since the released energy is less. These series are named Passion, Bracket, and Fund. Tip number 6. So what is the difference between electron affinity and electron negativity? While the two follow the same trends, they are indeed different. Electron affinity is the amount of energy released when a bond is formed, while electronegativity is a measure of an element's tendency to attract electrons, indicated by a value on the Linus Pauling electronegativity scale. Tip number 7. And next we'll look at Lewis structures. Here we have ammonia, whose Lewis structure consists of the bonds shown between the central nitrogen atom and the 3 hydrogen atoms, as well as the 1 lone pair. In ammonium, however, we must also include brackets as shown, as well as the charge, since it is an ion. Tip number 8. In resonance structures, there are even more things to remember to include. The example here of the carbonate ion CO3 2- is missing two important things required for all resonance structures. The first is that the non-bonding electron should not be drawn on non-central atoms, since we can never be sure how many electrons each atom has at a given time in a resonance structure. Your teacher will be very disappointed in you if you include them, and they will never let you live it down. The second is that we must include the letter R on the bottom right to indicate that the Lewis structure is of a resonance hybrid. Tip number 9. Electron domain geometry is different from molecular geometry. In the example of water, the electron domain geometry is tetrahedral since it has 4 electron domains with a molecular type of AX2E2. However, the molecular geometry is bent or nonlinear with a bond angle of 104.5 degrees due to the effect of the different amount of pulling by lone pairs. The molecular type is still AX2E2, however. Tip number 10. So what are van der Waals forces anyway? They are a collective name for the following intermolecular forces of attraction, or IMFAs. Hydrogen bondings, which is actually a misnomer since it is a force of attraction, not a bond, dipole-dipole forces, and the London dispersion forces. Hydrogen bonding is the strongest at approximately 5% the strength of a covalent bond, and London dispersion forces are the weakest but are present in everything. Here's an example of dipole-dipole forces. So on to an example question. Which forces below are van der Waals forces? This is a trick question. You may think it is only A and B, however the correct answer is all 3. This is because the dipole-induced dipole force is simply an explanation of the London dispersion forces which form due to induced non-permanent dipoles between molecules. Category F is about correcting mistakes concerning transition metals and hybridization. These are examples of colored transition metal compounds, and this is a hybrid. Not that hybrid. We will be talking about orbital hybrids. Tip number 1. In transition metal electron configuration, the 4s shells are filled before the 3d shells. This is because of the overlap of the orbitals due to the 3d shells being higher in energy than the 4s shells. This means that if we take nickel as an example, the electron configuration is argon 4s2 3d8, right? Well, that's wrong. The electron configuration is to be written in numerical order, meaning that the correct electron configuration of nickel is argon 3d8 4s2. When electrons are removed from transition metals as in creating ions, however, the 4s electrons are removed first. Tip number 2. What is the electron configuration of chromium? Well, chromium appears to have a full 4s shell and 4 3d electrons from its position on the periodic table. However, for the reasons of filled shells yielding greater stability, the electron configuration is argon 3d5 4s1, as the expected second 4s electron is instead the fifth 3d electron. This is the same for the other elements of this group, molybdenum, tungsten, etc. This is also true for copper, with electron configuration argon 3d10 4s1, and the other elements of that group, silver, gold, etc. Tip number 3. Now onto hybridization. This is the structure of sildenafil, commercially sold as Viagra. So what is the hybridization of the circled oxygen atom? Well, it makes one bond with each of the two carbons, so it must be sp hybridization, right? Well, wrong. Oxygen only makes 2 bonds in this diagram, but it still requires a full octet. This means that we must assume that it also has 2 lone pairs or unbonded electron pairs for the other 4 electrons. Therefore, the hybridization is actually sp3.
Category G is organic chemistry. So this is probably the last unit in your chemistry course, and hopefully with the tips that we have for you in this video, you won't feel like you're dying before your chemistry exam. So tip number 1 is the isomerism of butane. On the left, we have how we would normally draw butane with its 4-carbon chain, C4H10. On the right, we have isobutane, an isomer of butane. This should not be confused with propane because it seems like it has 3 carbons. Tip number 2 is the 1 in certain prefixes can be dropped. So here we have a 3-carbon chain with a ketone and a bromine. Now we would think that this is 1 bromopropanon, but we have to be careful. In this case, it is simply bromopropanon. If you look at it this way, bromine can be added to either terminal carbon and would still occupy the first position. Therefore, adding 1 would be redundant. Another area where you may be able to drop the number is if all the carbons except 1 are already bonded to 4 things, and therefore there's only 1 available place to add a group to the certain carbon that's left. Tip number 3. So, carbon makes how many bonds? The answer is 4. Carbon will always only be bonded to 4 things, so be careful when you're drawing your organic structures. Let's take the example of 3,3-dimethylpentane. Here we have the structure, but there is something wrong with the structure. I challenge you to pause this video and see what you might find wrong with it. Now, you may have noticed that the central carbon is actually bonded to 5 things, violating the fact that carbon makes only 4 bonds. This is not possible as carbon is bonded to a methyl group above and below, a carbon to the right and left, and is bonded to a hydrogen. Therefore, the correct way to draw this 3,3-dimethylpentane is as such, with the central carbon bonded to 1 methyl above and below, and 1 carbon to the right and to the left.
Look at that one, oh my god.